Okay, so yeah, I'm presenting on zero-knowledge differential privacy, which is a way for two-way trustless data sharing between a curator of data and people who want to make aggregated queries on a set of data. So first, I'll start by sort of motivating this problem. This is not a fairy tale, this is a real-world story of something that happened. So in 2009, Netflix realized that they could improve their movie recommendation algorithm massively if instead of just working with the ML engineers in their company, they created an open competition for everyone in the ML community to have a go at trying to produce the best movie recommendation algorithm. Of course, this was a great idea, but Netflix has a lot of private data about people. So what they did was they completely pseudo-anonymized it. Names, addresses, any personally identifiable information was hidden, so you couldn't see personal identifiable information associated with movie ratings in this database. They then released it into the wild and let people have a go at producing the best machine learning algorithm. The problem with this was that hackers were able to use auxiliary data sources like the IMDb database and match up movies that people had rated on IMDb to their ratings in Netflix. And what that meant is they could then trace back exact individual users and their names from the IMDb database, and personally identifiable information was able to be extracted from something that was supposed to be completely private because of pseudo-anonymity. So this kind of reconstruction attack is inevitable in almost any sort of scheme where you are making infinitely many queries and you're giving perfectly accurate answers about data, which is where differential privacy comes in. So this whole conference is about zero knowledge, and zero knowledge has a slightly different use case. I mean, this is a very high level sort of like analogy. You can say that, you know, ZK can say that I have some data, I can prove certain properties about it without revealing what that data is. Differential privacy is about something else entirely. It's about taking aggregate queries on a database and saying, you know, I won't give you the exact answer, because if I give you the exact answer, you can use some other public data that's floating around on the internet and reconstruct and do reconstruction attacks. So I will give you a slightly inaccurate answer. How this works is essentially, if you make an aggregate query on a database, for example, you might be asking, you know, you have a database of users and their screen time, and you ask, what's the mean screen time of any user? You might have a version of a database with John in it. And to protect John's personal privacy, what you want is when someone makes a query to database D prime, they should never be able to tell whether John was in that database or not. And so instead of returning the actual mean of that database, you return a sample from a slightly noisy distribution where the mean is, well, the mean of the distribution is the mean of the database. So you have a distribution associated with John being in the database and a distribution associated with John not being in the database, and you want the difference, the Renyi divergence to be specific. You want the divergence between those two distributions to be below some privacy threshold. That's the essence of differential privacy. You have neighboring data sets, and you want it so that any person who's querying a database can never tell whether the state of the database is what it actually is or some neighboring state. This is the formal definition. About half of you had already come across differential privacy, so I'm sure you've seen this definition before. But essentially what it's saying, what I just described was what's called epsilon zero differential privacy, which is where you are saying that the probability that a mechanism, the output of a mechanism on a database is in some set of outcomes is bounded, well, okay, epsilon is very close to 0, so epsilon is close to 1. So it's saying it's very close to if there was some neighboring database and you took a query on that database and it was in the same set of outcomes. And then plus delta is a term to sort of increase the bound. And what that means is basically there is a 1 minus delta probability that the database is epsilon differentially private. I mean, this is going into the weeds of it, but I hope that this example gave you a sense of what differential privacy is trying to solve. What qualities does differential privacy have? Well, it means that once you've taken a query of this database and you get a noisy output, it's completely immune to post-processing. So regardless of what someone does after that, you know, they could take the mean and they could then run it through as many machine learning algorithms as they want. They could try and use the IMDb reconstruction attack. They could use some private data that they've collected. It doesn't matter. They will never be able to reconstruct individual information about that data because it was noisy enough that the probability of them doing that is below a certain bound. It's composable. It's composable with the caveats that if you make more and more queries, your data becomes less and less private. I mean, this is just the way these things work. That if you take if you have an epsilon1 bound on a particular query and an epsilon2 bound on another query, and then you're using both of the results of both of those queries, and you're composing them together to get some more information, the bound on the privacy of the composed result will be epsilon1 plus epsilon2. So it gets worse over time. So that is definitely a caveat to think about in terms of like what the use cases of this technology are. And as I said, it's robust against the kind of Netflix attacks that I was talking about before. So this is how it works at the moment. I mean, in terms of real world, like the US Census uses this for the first time. I think the most recent US Census used a differentially private database. The UN uses it for their information on like the Rwandan genocide and families which escaped. Anywhere where individual privacy is critical, organizations are already using differentially private databases. And these are the reasons why. The problem is this is one-way trustless. So if a research team is going to a database held by the UN, and then they're getting this noisy data back, they trust that the UN is giving them the right noisy data back. And you can easily construct scenarios in which this might not be the case. And the holding organization, the data curator, might have an incentive to treat certain queries differently. There might be people who they're biased towards, who they might want to give more accurate results to, and people who they don't like, who they want to give less accurate results to. And you would never sort of know. There's no guarantee that the data is pure, that they're not meddling with the data inside. There's no guarantee that the amount of noise they're adding is minimized. We have a mathematical bound on, we've agreed that, okay, you need to add this much noise to protect the individual's privacy. Sure, you can add that much noise. But how do you know they're not adding any more? So what I did in the hackathon project in Paris was essentially just add in, the difference between these two slides is there's a ZK proof at the top of the private answer that you get. So you do a ZK proof of the noise computation. And we don't need to go into the depths of all of this, but the reason I've had the slide is so you can look into the paper that I was using the equations from for differential privacy. In essence, what I was doing is you have a... Well, the noise that you're adding is coming from a Gaussian distribution, and you can work out the exact amount of variance on that Gaussian distribution that you need to maintain privacy at a certain level. And you can do that variance calculation within a ZK proof. And so that's what was happening there. And to summarize, ZK differential privacy is a way for two-way trustless data sharing between an organization that is curating some data and queries that are trying to use that data. Both parties care about the anonymity of individuals in that database, but ultimately you want to be able to analyze data in a way that is safe to the individual inside, and you want it to be in a way that both parties don't have to trust that the other is doing things the way they should be doing, and this is why ZK can be used for something like this. What I would be very keen to hear is if people have ideas for sort of like areas where they think this could go further, and applications in which they feel that this kind of stuff can be used in. And I'd love to chat to you afterwards about that. Happy to take any questions now.
Thanks a lot. Do we have any questions? Yes.
Hi, thanks a lot for the talk. So I just have a quick question about the randomness. So I understand that in providing zero knowledge guarantees in ZKPs, that randomness is out of band. So it's trust, in a sense, it's trusted randomness. Could you maybe talk a little bit about what the assumptions are around how that randomness is seeded and how that affects the security proofs?
Yes, for sure. I think that's the most difficult bit of the ZKDP paradigm is doing provable randomness. That's not a bit that we tackled inside the one-day hackathon project. In fact, what we were doing was just the seed of the randomness was outside of the ZK proof, and everything else. So from the random seed onwards, everything else was in the ZK proof. So that's not a bit that we've cracked yet, basically.
Follow up. So, like, just thinking about it right now. Is it as trivial as saying the querier sends a random seed and the response is the PRF the verified PRF output of that seed as the seeded randomness as part of the thing? Or because it kind of gets a bit weird, right? Because you sort of would then need two proofs. One of them would not be zero knowledge and the other one would be. I'm just spitballing here, but I don't know if you've thought about this stuff.
Yeah, this is not an aspect of it that I've had time to think through, but I could imagine like the verifiable randomness coming from the user being a potential solution to this, for sure.
Yes.
Somewhat of a related question, which is like if the goal is to make this into like a bulletproof setup, right? You'd also want to reason about not only the process of noise addition, but also like exhausting the privacy budget, right? So you don't want to have basically infinite attempts, right? So and then you basically, I think, would close the loop. So what are your thoughts on that?
I think this is spot on. This is a question of use cases. Then, like it comes back to like this is a paradigm that you would want to apply somewhere perhaps where, so the way the UN applies it is they will allocate an amount of privacy budget to each team that is got access to this data. And once they've used up that privacy budget, they can't access the data anymore. So, a research team could choose to make one extremely accurate aggregate query about the mean age of everyone in the US. And they would get a very, very precise answer that's correct to, thousands of decimal places. That might not necessarily be the best use of their privacy budget. They could also make a bunch of less accurate queries. One area where I think this is particularly interesting is dynamic data. So if you have a database where you have some kind of level of churn, where the data is sort of expiring and you're sort of ejecting some data from the database and putting in new data, then some of those privacy guarantees can sort of be like reset. It's almost like you could refill your privacy budget. And I don't know, I haven't looked into if anyone's working on this, but I think that would be a very interesting direction.
And people talk about epochs and data that's like moving over time, that sort of thing. Yeah. Mm-hmm.
So just a question related with kind of possibly an extension. Have you ever thought about how to make the query itself private? So to have everything private and also the query itself?
Oh, you mean like a proof of API call or something like that?
No, I was thinking more like, for example, maybe using multi-party computation or something for the query itself to be private, so not to disclose the query itself. I don't know.
Right. To not disclose what the query is to the data curator.
Exactly. Mm-hmm.
That is definitely a direction. So that is not one in which I've explored. But this is another area that would sort of coming back to whoever was talking about closing the loop. There are many aspects of this. So I think back on the slide, the bit I tackled was the bit I felt that was most needed, which is the ZK proof on the private answer, that arrow there. But yes, essentially every single arrow in this space, even this bit, how are you collecting data from the generators and putting it into the database? This is where we come back to like hardware attestation and sensors and all this kind of thing. Every arrow here needs to be like sort of thought about. There's a lot of work to do in terms of closing the whole loop.
All right. So I think we have to wrap up. So thanks again, Manuj.
Thank you very much.